Did we include it? Okay, hello everyone. It's my pleasure to introduce today's speaker, Professor Bradley Howard, an assistant professor at the Institute for Quantum Computing and the Department of Electrical and Computer Engineering at the University of Waterloo. Professor Howard's research focuses on cavity optomechanics, superconducting circuits, and their quantum information applications. He holds a PhD in physics from the University of Alberta and has received numerous awards, including a prestigious Banting postdoctoral fellowship. So please join me in welcoming Professor Howard. Hello, Professor Howard, welcome.
Thank you. Yeah. Can you hear me okay?
Yeah, I can hear you fine,
Good.
yes.
Great. All right. So I'm gonna try to not share my screen. Let's do that. Good. Okay. Slides. Perfect. Okay. So you can see the slides. It's in the right presenting mode and everything.
Yes, yes.
Great. Okay. Great. Okay. Thank you. Thank you very much to the organizers for this workshop for inviting me. So as was mentioned in the introduction, my name is Bradley Hauer. I am a professor at the University of Waterloo in the Electrical Engineering Department and the Institute for Quantum Computing. And I just recently started, so I've only been here for a few months, but yeah, I'm very excited to talk to you a little bit today about how you can, well, first of all, I guess what kinetic inductance is in superconducting systems, as well as how you can account for it in simulations when you're designing your superconducting circuits. So yeah, so to jump in, see. Great. So I'm going to give a brief introduction to kinetic inductance, talk a little bit about a specific kinetic inductor that, or a specific superconductor that exhibits kinetic inductance called granular aluminum that I've worked with in the past. Then I'm going to basically go into a COMSOL demo where I'm going to talk about half-wave resonators and how we can see how kinetic inductance can affect simulations of those type of objects. So first, I just want to start with the Drude model. So I'm sure some of you have heard of this model before. It's basically a very simplistic way of describing conductivity of materials such as metals. So the way you write your conductivity is something like this. So N is the number of charge carriers, E is the electric charge, tau is basically some scattering time of these charge carriers. They move through the metal they're in. M is the mass of these charge carriers, and then frequency is the frequency we're looking at. So this is a complex quantity here, so we can always express it in terms of sort of a real and imaginary part. So I'm going to call the real part sigma 1 and the imaginary part sigma 2. So you can work through, make the denominator real and find what each of these different quantities are. So we basically have, again, the sigma 1 is the real part, which corresponds to some sort of resistive component of the conductivity. And then we have the sigma 2, which is the imaginary part or the reactive component of this conductivity. So what we find is for conventional metals or sort of normal conductors, um, for the scattering times associated with them, for most frequencies, we have this omega tau is much, much less than 1. If we put that back into these equations, what we find is that these metals are essentially resistive. So we've got some sort of DC conductivity associated with them. It's frequency independent, and it has a non-zero value. And then this reactive part is actually 0, just because the fact that there's this omega tau in the numerator. However, if we think about superconductors or at high frequencies, or potentially both, this omega tau term becomes quite large. And so what happens here is essentially the resistive part goes to 0. So these become very, very highly non-resistive materials, even at high frequencies. And we actually get this reactive part now becomes non-zero. So what I'm going to try to convince you of is that this additional reactive part of this imaginary part of the conductivity is going to lead to what looks like some amount of inductance, which would be called the kinetic inductance. So the kinetic inductance is basically shows up in a system due to the inertial mass of molar carriers. So it's a resistance to flow or resistance to current, which looks just like our geometric inductance, which is a resistance to current due to the changing of the flux in the system. So what we can do is we can write our impedance of our conductor or our superconductor, conductor, whatever we're interested in, as this here. So it's just this sigma is the conductivity. This is the length of whatever that conductor is, and then the width and the thickness are down here. So that, if we write in terms of our sigma from the previous slide, so this complex conductivity, we find as something like this, where we can now write this as basically a resistance and a frequency times some sort of inductance. So again, for superconductors, remember from the previous slide, we expect something like sigma 1 is going to be very small compared to sigma 2, which is going to be non-zero. In this case, what we find is that R, the resistance, is going to be very close to zero. So this tells us that AC currents will flow with very little resistance in superconducting circuits. And finally, we get this inductive term, which is proportional to, again, the sigma 2 that I mentioned before. In the case where sigma 1 is much, much smaller than sigma 2, we can actually simplify this. And so the kinetic conductance just really depends on the frequency of the system, the excuse me, the dimensions, as well as this sigma 2. So again, this is some inductance that's shown up just from the fact that we have some reactive part or lag in our circuit, sorry, conductivity of our circuit. Okay, so I mentioned this Drude model before, but really the real way to model these conductivity in superconductors is what's known as using Mattis, or what is known as Mattis-Bardeen theory. This is actually a very complicated, so I'm going to write down just what those two sigmas look like in terms of the normal conductivity. They're these massive, very ugly integrals that in general you'd have to solve for specific conditions. But we're actually just going to focus today on a simpler case. We're going to look at temperatures much below the critical temperature of our superconductor, so much, much below the temperature at which it goes superconducting. In this case, we can write the gap as just 1.76 times kb times that critical temperature. This is a general result of BCS theory. And we're also going to look at frequencies that are much less than the gap energy. So in this case, what we find again is that this sigma 1 goes to zero, as we expect. That means we get low resistance in our superconductor. As well, we get a finite sigma 2, which is going to lead to a kinetic inductance that looks like this. And this alpha parameter is just a parameter which depends on the critical temperature of the superconductor, its resistivity in the normal state, and then some fundamental constants. And the rest just basically depends on the geometry of our structure. So, this is what we're going to focus on. So our conductivity is going to be basically dependent on this alpha parameter divided by frequency. So there's some frequency dependence. And then our kinetic inductance, again, depends only on the dimensions of the system, plus this alpha parameter, which depends on the superconducting properties as well as some fundamental constants. Okay, I just want to point out too that kinetic inductance is actually known normally to be quite nonlinear. So what I've been talking about up to now is basically the linear part of the kinetic inductance. So it's the kinetic inductance for zero current. But if you go to high enough currents, there's some above some or near some I star for this material. What you'll find is that you get some nonlinearity that comes up the system. So this is what actually makes kinetic inductance fairly interesting for a number of different systems. What that lets you do, you can make kinetic inductance detectors. So there's a number of different researchers who have done microwave specifically detectors, but all sorts of different frequency detectors using kinetic inductance based superconductors. You can also use them for amplifiers. So this nonlinear element allows you to do 3- and 4-wave mixing, which can then generate amplification in these types of circuits, which is a very hot topic of research lately, especially in the frequencies of, especially at microwave frequencies, where people are interested in amplifiers for quantum technologies. As well, with this nonlinearity, you can actually make it large enough that you can start to think about actually making qubits out of these high kinetic inductance circuits. So instead of a Josephson junction providing your nonlinearity is now provided by a high kinetic inductance superconductor. And so, often what you need is a specific type of superconductor that has high kinetic inductance. So I've given some examples down here. So the common ones are niobium nitride, niobium titanium nitride, or this one I mentioned at the first slide, which is those granular, which is also what's being used, I believe, in both of these two over here. Okay, so granular aluminum, what exactly is that? So granular aluminum is aluminum that is basically exposed to some oxygen while it's being deposited. So what happens is instead of forming a nice pure film of aluminum, what you get is basically little islands of aluminum that live in an aluminum oxide matrix. So what you can kind of think of this as a whole bunch of little tiny Josephson junctions. So there's aluminum, aluminum oxide, and they're all coupled to each other. So what you can show is that for certain amounts of, or basically as you increase the oxygen content, you're going to increase the resistivity of this the system when it's in the normal state. So this is the bottom axis here. So basically this axis is telling you how you increase the oxygen content. What you find is some very interesting things. First of all, even though you've introduced this insulator into the system, you still have a superconductor. It's actually even better superconductor than it is in pure state. So the pure aluminum has a TC of about 1.2 ish in this band here, basically. But as you increase this oxygen content and increase this resistivity, what you find is you actually increase your actually, let's see if I can get a laser pointer. You can actually increase your conductivity up to a certain point. So they call this the superconducting dome. You can more or less double the critical temperature, and then eventually, as you make it more and more resistive, it essentially turns into a resistor, and eventually that TC goes away. But people have shown that you can make circuits out of this. So, for example, in this case, this is a special circuit. We've got basically a capacitor up here, and then some inductor formed out of granular aluminum. The reason this is done is because as you increase the resistivity, as we saw previously, you also increase the kinetic inductance. So here is some examples of increasing resistivity as well as seeing the kinetic inductance go up and the critical temperature going up as well. So again, in this circuit, what they're doing is they're making this inductor out of a high kinetic inductance material, and that allows you to just make this inductor smaller than you would if you were just relying on the geometric inductance. So this is a very interesting material, basically because it has a tunable kinetic inductance. So you can tune what the kinetic inductance is basically by changing the content of the oxygen as you deposit the material. So I've actually done a bit of work with this. So I just want to show a quick slide here talking about some resonators that I measured. So these were what I call spiral resonators. So these are just basically coiled up single layers of superconductor. So we did some measurements for what we call clean aluminum at a couple of different thicknesses, so 100 nanometers and 200 nanometers, and we're basically measuring versus frequency, their quality factor to see, excuse me, how well we could do in making these circuits. We then started playing a little bit with adding some oxygen. So we added a little bit of oxygen, got 20 microohm centimeter granular aluminum, and then also 90. What I really want to point out here is for these light blue things, they're actually the exact same geometry as these other clean aluminum resonators. And what you see is that the frequency has shifted significantly lower. So the reason why that's happening is because as we increase our oxygen content or increase our resistivity, what we're doing is we're increasing our kinetic inductance. And so when you think about an LC circuit, increasing your inductance will decrease your frequency. So we're getting exactly what we expect. And I'm going to talk a little bit more about how we can actually model this in simulation when we're designing these circuits, which is very important for being able to include these types of interactions. I just want to point out too that we actually went to some thicker aluminum and some higher resistivity, so higher critical temperature. We actually saw an improvement in the quality of these circuits. So there was definitely something going on at these higher frequencies that the quality of circuits improve as you go to higher oxygen content. So there's something interesting going on here that we're still trying to understand. But I just wanted to point out that I've done some work with this, and so I have some idea how to simulate these types of devices. Okay, so that's kind of the brief introduction to kinetic inductance. So now I want to go on to working towards a demo, basically, to show how you do this in COMSOL multiphysics. So COMSOL, if you're not familiar, is a finite element analysis simulation software. Basically, it takes problems and it breaks them up into tiny little pieces, and then you solve these tiny little pieces numerically and stitch them all together to make a big solution. So you can do this for a number of different types of physics. So what COMSOL is really good at is solving in all sorts of different geometries, different types of solvers, so stationary, time-dependent, frequency-dependent, which is an eigenfrequency, which is what we're going to use today. But it can model a lot of different physics, so electromagnetic fields, acoustics, heat transfer, structural mechanics, fluid flow, and chemical reactions. But one thing that actually is not very good at is superconductivity. It doesn't actually have any sort of module, at least as far as I'm aware, to model superconductors. So we're going to talk about today about how we can kind of trick it into being able to model superconductors. I just want to point out too, just there's a number of different packages and models and COMSOL that you can use. For example, the ones we're going to look at today are these models over here for looking at electromagnetic fields, specifically the RF module. There's also multi-purpose modules they call them, basically for in this case optimization, as well as interfacing. So MATLAB, Live for MATLAB allows you to basically run simulations through MATLAB, which is very powerful for a number of different instances, as well as the CAD import module, which allows you to import complex geometries through CAD software like Autodesk, for instance. Um, okay, so let's move on to our example. So what I'm going to talk about today is what's known as a half-wave resonator. So over here, this is an example of a half-wave resonator in a coplanar waveguide. So what happens here is basically you have some long strip of say circuits or superconductor in this case. And what you want to do is you have an open circuit on each side in this case. What happens is the field will then be maximized at each of those spots in order to basically create these standing waves in this circuit, which leads to a frequency basically, which is some integer number of half waves in the system. So the frequency will be given by some integer times the phase velocity divided by the length of that circuit. And then we're going to get fields that basically look sort of like these sinusoids in this structure. So for that n equals 1, you get something like this. For that n equals 0, you get something slightly different. So what I want to make this out of is some microstrip line. So this is basically a superconductor or metal based on top of some sort of dielectric, which is going to be some distance d away from the ground plane. There's going to be some width w, some thickness t, and then we're going to have some epsilon r is going to be the dielectric constant or the relative dielectric constant of our dielectric. So what you can find is that for if this width is much smaller than this plate separation or this ground plane separation, you get an effective dielectric constant you can write like this, and then in a geometric inductance. So that just the inductance, if this was a normal metal with no kinetic inductance, would be given by this equation here. So let's look at a quick example. So let's imagine we want to calculate the length of a microstrip half-wave resonator on top of sapphire, which has epsilon of about 10. Let's imagine we're going to have a 3-micron width, a distance from the ground plane of about 30 microns, thickness of 100 nanometers, and what length do we need in order to get its fundamental frequency to be 100 gigahertz. So in order to do that, we basically have to first calculate our effective index refraction. So we use that equation on the previous slide. I put the numbers in here. We get something sort of close to 5.9. And then what we can do is we can use that to calculate the length of the circuit. So we know what frequency we want. So we rearrange this equation for length. So then we just have the speed of light up here divided by the twice the frequency and then the square root of that effective index refraction. So what we find is we want a resonator that's on the order of about 0.6 microns. Okay, so let's switch to COMSOL now, see if we can actually simulate this. So I'm going to try to do that now. Can everyone see COMSOL now?
Yes, we can see it. Yes.
See it? Okay, great. Okay, so I'm going to basically, for most of the rest of the talk, build a model in COMSOL. So I don't know how many people are familiar with COMSOL, so I'll try to go relatively slow and build from the ground up, make this simple model, and then continue to sort of play around with the parameters and just sort of work through the model itself. So if you start up COMSOL, you're going to get something that looks like this. So it wants you to basically, start building your model. So normally what I do is I go model wizard. It wants you to pick your dimension. So we're going to do a 3-dimensional simulation. So I'll pick 3D. It then wants you to pick which physics you want to use for your simulation. So in this case, we're going to do radio frequency or RF. And then we want to do electromagnetic waves in the frequency domain. So we're going to look at frequency dependent simulation. So we will add that to our simulation. Next, we want to pick a study. So the study basically tells you what you're going to look at. In this case, we're going to try to solve the eigenfrequency of this system. So we want to pick the eigenfrequency study. So once we picked all that, we pick done. And then COMSOL will go ahead and basically populate that model for you. So it brings you to this user interface. So basically, the workflow is to sort of work down all the way to the bottom here where we're going to run this study. So we're going to start by just defining some parameters. So we know from the previous slide, we want a width of about 3 microns. So we can put that in and then give it a bit of a description. So COMSOL will actually let you write in these units. So I just said 3 microns and then the value would just be 3 times 10 to the 6 meters. So it gives you the SI unit over in this panel here. We said that we wanted that length to be about 0.16 or 0.617 millimeters. And then we wanted the thickness to be 100 nanometers. So I can put each of those individual units in, and it's always going to know exactly what I'm talking about. I'm just going to keep labeling them so I can keep track of things. We then wanted that ground plane to be about 30 microns. So let's call that the ground plane distance. And then finally, we wanted that relative dielectric constant of our dielectric. So we're going to do sapphire. So relative. Okay, great. So we have our parameters set up now. So these are the parameters for our system. The next thing that we need to do is we need to build the geometry. So we'll go to the geometry tab. There's all sorts of different geometries you can do. You can make cones, blocks, cylinders. There's all sorts of different helixes, lines, all sorts of interesting things. We're going to basically stick to simple stuff for this demonstration. So I'm just going to basically use rectangular blocks. So block one, we're going to call that the substrate. It's going to have a width. So it's going to be 2 times d plus the width of this microstrip. So that basically gives us spacing of d on either side of that in the x direction. We're going to do the same thing in the y direction, but we're going to give it the length now of the strip instead. And then finally, we're going to make the height equal to the distance, or d, this difference between the ground plane. We'll see why in a second. So I'm going to base that on the center. So it's going to center that on the center of the block, put the center of the block on the origin, and then I'm actually going to displace it by d over 2. So that puts the top of that block in basically the xy plane. So we build that. We see over here, we get that block just like we defined. It's got some axis. So you can again see that the 0 is right at the top here, and then we're going to have it go down by 30 microns in the minus z direction. Oops. There we go. Okay, so let's keep going. We're going to make a second block, which is going to actually be for the air of the system. So we need to make sure we have the surrounding air here. So this is going to be exactly the same, except I'm going to offset it now by plus d over 2 this time. So now basically it's going to stack on top of that other block. And then the last thing we need to do, I'm going to duplicate this again just to save some time, is we want to make our microstrip. So let's make our little microstrip. So in this case, I just want it to be the width, the length, and the thickness, and I'm going to offset that by the thickness over 2. So I'm going to build that. You don't actually see that it's been built, but what you can do is best because it's basically sitting inside these 2 other domains. So what I can do though is I can get rid of this one here, and so you can see there it is sitting inside. So if I were to build the previous, you'd see that it wasn't there, and then if I go build it, you can see the microstrip shows up in there. So great. So this is our geometry of our structure. This is exactly what we're hoping for, so that's good. Basically, the idea is we have this microstrip. It's sitting on some sapphire substrate, and then that basically has a distance of 30 microns to each of these individual boundaries here. So next thing we need to do is specify the materials. So we don't have anything in this set up in here already because we basically just started this model, but we can add a new material. So we're going to add a few different things. So first of all, I'm going to add air. So basically, it's going to ask me to specify where the air is going to be, so which domains it sits in, and then give it some material properties. So I'm going to get rid of all those domains. I only want this top domain to be air. So there we go. When you click on something, it highlights it as blue. And again, domains basically mean like 3-dimensional or volumes in this situation. So for air, how we're going to model that, it's basically going to have an epsilon, relative permittivity of 1, a relative permeability of 1, and a conductivity of 0. So it's a very simple material, but it's basically this will emulate vacuum for our electromagnetic simulations. So now we can duplicate this to make another material. So in this case, the next one I want to do is sapphire. So that's going to be our substrate. So it's very similar to air, except now, so we're going to leave this the permeability the same, the conductivity the same, but we're just going to change the the relative permittivity to what we wanted for our sapphire. So that's that value we specified, um, excuse me, in our parameters earlier. So that's good. So our last material that we need, oh, sorry, I gotta, yeah, specify this. So this, I don't want that to be in the same spot as the air. I now want that to be the substrate. So now this is this bottom part here that's been highlighted blue. So air in the top, and then sapphire substrate at the bottom. And then we need one more material. So that's going to be our superconductor. So let's duplicate that again. So I'm just going to call this superconductor. So what I'm going to do first is I'm not actually going to make it a superconductor. I'm just going to make it a really good conductor. So basically a perfect or close to perfect conductor for the sake of this demonstration. So I'm going to change the relative permittivity back to 1, permeability 1, and now the conductivity, I'm just going to make that artificially very, very large. So 10 to the 12 cm per meter is a very high conductivity material. So that's going to look essentially like a perfect conductor for our purposes here. And again, I need to clear this selection. I need to go back and I need to pick that microstrip. So now we've got our air surrounding, our sapphire substrate, and then on top of that, we have our microstrip resonator, which we specified as its conductor. So good, we've got our materials now. So the next thing we need to do is create a mesh. Or sorry, let me just go through this quickly. I'm not actually going to change anything in the solver, but in the physics. But basically, what it's saying is it's going to solve the electromagnetic wave, so essentially Maxwell's equations inside all of the domains. It's going to solve the wave equation. On the boundaries, what it's going to do is it's going to create a perfect electric conductor. So this is a way to efficiently simulate things, as you always normally put perfect electric conductors on your boundaries. So this is kind of why we chose this distance to be this 30 microns. So this is effectively now our ground plane here. What we're going to see is there's essentially ground planes everywhere now, though, which is going to tweak our simulation a little bit. But to the level we're actually interested in, it's actually not going to affect it that much. So we're okay with that. And then the initial values, we're just going to set everything to be 0. It'll excite the system and calculate its eigenvalues. Okay, so next thing we need to do is to include our mesh. So the mesh basically tells us, I mentioned before, this is a finite element solver, so it's going to solve physics in tiny little pieces throughout the system and then stitch them all together. So the mesh tells you how small those tiny little pieces are that's going to solve while it's doing its iteration. So basically, you need to make this small enough that it can accurately depict the system or solve the physics for the system, but not too small that you run out of basically computational power to solve the problem. So it's a bit of a art form and a bit of a balancing act, but I'm going to quickly go through a simple way to do that for this relatively straightforward structure. Okay, so there's a number of different meshes, just like geometries, both for boundaries and domains. So what I'm going to do is I'm going to actually start with a triangular mesh. So a triangular mesh is for a boundary. So what I want to do is do that for the bottom boundary of this microstrip resonator. So I'm going to zoom in. What I'm going to do is remove. So I'm going to get rid of that surface, the top one there. So then now what I can do is I can go in with this free triangular mesh. So I'm going to call that microstrip bottom mesh. And I select that bottom boundary. And what I also want to do is I actually want to include a size node. So there's lots of different things you can control with these meshes. What I often like to do is just control the maximum element size. So you can do that by adding a size node. You go to custom and then set the maximum element size. And I generally set it to some dimension of the system. So in this case, I'm just going to set it to the width of that of the microstrip. So I can build that mesh, and what you see is this nice mesh that's going to run all the way along the system, and it's going to give us excuse me, a boundary mesh for the structure. What you can see over here is that it gives you, as you build these meshes, it's going to tell you how many elements there are. So there's 824 boundary elements and 418 edge elements. Okay, so great. That forms a boundary mesh, but what we actually need is a three-dimensional mesh. So we do that creating what's known as a swept mesh. So what that'll do is it'll take a boundary mesh and basically sweep it through a structure to make it three-dimensional. So what I'm going to do here is select the domain I want. So I want the microstrip, so domain 3. I also need to specify the source face, which is basically going to be that face I just meshed. Good. And then I need the destination. The destination, so the source will be the top, the destination needs to be, sorry, the source is the bottom, the destination needs to be the top. So I'm gonna have to actually undo um, the hiding things, and then rehide the top of the. So the top of the box is gone, but I still can see the top of the microstrip. So I can now go in and I can select that um, boundary. Sorry, okay, I got activated over here. So select boundary, and then I can build selected. So now what it's done is it's actually swept that mesh through my microstrip resonator. I now have 824 domain elements, so 824 volume elements, and then more boundary and edge elements. And so this swept mesh is, I should actually name that quickly. Let's call that microstrip mesh. So these swept meshes are actually really efficient for sorry for meshing very thin elements, so thin elements with large aspect ratios. And I actually wanted to point out too, you can add, so you can play around with this. The thing I like to play around with these guys is distribution. So you can add a distribution node. It actually automatically did distribution of one, but I'm just going to force it and make sure that it only sweeps one through here. So if basically this was set to five, it would have swept five different elements through. In this case, we just want one. One's enough. So we're gonna set it like that. Okay, so we need to continue with our meshes. So we're going to do a free tetrahedral mesh. So for our air, so this is basically just a three-dimensional mesh that forms from tetrahedrons. It's very good at stitching different meshes together. So that's why it's very robust and good at sort of building three-dimensional meshes for any arbitrary object. So let's do that for our air. So I'm going to again select the boundary. So air, sorry, select the domain, just air. And then I always like to add a size node so I can control the size. In this case, I'm just going to do sort of a predefined or like a default setting. I'm not going to use normal. I'm going to use coarser. So this is just some arbitrary setup. But basically, when you build it, COMSOL is going to do some thinking, and it'll essentially stitch all these meshes together so that it matches the mesh that was on the microstrip resonator, and then also makes a coarse mesh on the boundary. We don't have as much field. We don't care so much. So that's exactly what we want. One thing I will point out too is when you're meshing things in COMSOL, the order definitely matters. So the fact that I meshed this microstrip first and then the air changes how that mesh would evolve. Okay, so let's do the exact same thing. Actually, we can just duplicate for our sapphire. So let's call this sapphire. So we got to clear which domain it's using, and then we're going to make the bottom. So we've just basically swapped. So we're now making the mesh on the bottom. We still have this size node. Coarser is good, so we can build selected. It's going to build a mesh. And so now we have completely meshed our geometry with about 28,000 domain elements and then a whole bunch of boundary and edge elements. This number probably doesn't mean a lot to most of you, but I know for my computer, this is definitely manageable. This will run in a few seconds, maybe 10 seconds or so. So that's a good number of mesh elements for this demo. In general, you want to tweak your mesh in one way or the other, depending if you want things to run quickly or want more accurate. In general, more mesh elements will give you a more accurate simulation, but sometimes you may not have the time, the computational power to handle that. Okay, so we're almost done. So the last thing we want to do is we just want to set up our study. So we're doing step one, so it's eigenfrequency. There's a number of default settings that I'm not going to touch, but basically I want to change the number of frequencies it solves for. So I'm only going to do solve for one, basically because I know what I'm looking for. I'm going to set the basically the search is going to search for eigenfrequencies that, excuse me, I'm going to pick to be the larger real part. So it's only going to look for eigenfrequencies above 10 gigahertz. So I'm going to run this now. And I know it's actually not going to work the first time around because I need to change some settings in the solver. It only lets you, as far as I know, it only lets you get access to the solver once you run it once. So I'm going to let it run. It's going to give us the wrong answer, and then we're going to go in and fix it. Let's take a quick drink while that wait for that. So assuming I did everything correctly, this should finish up quickly. Good. Okay, so as I mentioned, we're gonna get the wrong answer. So it basically just gave us back our 10, sorry, our 10 gigahertz initial guess. So that's very unlikely to be right, unless we were very lucky and had the right simulation setup. But basically, what I'm going to go in is change one solving configuration. So go into the solver configurations, go to solution one, go to eigenvalue solver, and then I go suggested direct solver. I'm just going to change the solver from this Paradiso to mumps. So I don't know what these necessarily mean, but they're different types of solvers. I know that this mumps works well for the type of problem we're working on. So let's just rerun it with this mumps. See if we can get a better answer. So also I'll point out too that the simulation time was down here. So that first simulation took 30 seconds to run, and we'll see how long the second one takes. Hopefully it's a little faster this time. Good. So this one took about 20 seconds this time around. And okay, so the number of different things you can look at here. So the default of what it looks at is the electric field. So we can go look at where that electric field is. And so as we expect for our half fundamental mode of our half wave resonator, we have basically very little field in the center here. And then as we go to the edges, you can start to see some color show up. So this color basically tells you the field. So there's some field that exists on these edges, and that field is sort of arbitrary, but it gives you a relative scaling from this color bar over here. What we really care about those is eigenfrequency. So up in this top left corner, we can see the eigenfrequency. I'm not sure how easy it is to see on the screen, but basically what I'm reading is 101.98 gigahertz, so 102 gigahertz roughly. So we were targeting 100 gigahertz. We didn't quite get there, but we're not that far off. So this is about 2% error in between our simulation and our analytic model. That's I would say that's pretty good considering the analytic model has a lot of simplicity to it, and we're now starting to look at there's a couple of things going on here. First of all, the analytic model isn't perfect; it's not going to encapsulate everything, as well as the simulation is done as a finite volume. So the analytic model is some sort of an infinite structure, so infinite error out here, infinite or at least infinite in these two dimensions for our ground plane. So there's a few things here that are basically causing us to have some issues. What I really quickly want to show before I move on to the kinetic inductance stuff is I can actually play around with the geometry a little bit. So if I make the inductor a little bit narrower, so I just change it to 2 microns. What we know or what we expect from our equation is that it shouldn't change the frequency too much. The frequency of a half-wave resonator should only depend on the phase velocity as well as the length of the system. So if we go back, it's now still running, but hopefully it should finish in a couple seconds. We will be able to see that changing the geometry of our system actually didn't really affect things too much. So it's got quite a bit more, because I set the mesh to be equal to the size of the width, it's actually got quite a few more mesh elements. Anyways, we changed our frequency, we changed our width, and we've now got a frequency of 102.32 gigahertz. So it's very, very close. I'm going to set that back to 3 microns. And then I'll change, so let's change the thickness too. So we can change the thickness from 100 nanometers to 50 nanometers. We'll run that one more time, and we'll see that hopefully, again, changing both the width and the thickness doesn't really affect our frequency of our resonance. Then we can make the mesh a little bit coarser to make this run a little faster, but hopefully it'll be finished soon. Great. And so again, our frequency is slightly different. It's 101.7 now, but it really hasn't changed by that much by changing the geometry of our structure. So I'm going to change that back. Okay, good. So we did this. We know how to simulate superconductor, basically perfect conductor resonators. So how do we actually introduce the kinetic inductance here? So the way this is done is we go and we say, okay, well, let's say we made this resonator out of, so I won't actually go into presenter mode, but let's say we made our resonator out of granular aluminum that had a resistivity of 100 micron per centimeter and a critical temperature of 2.3 Kelvin. So we can calculate this alpha parameter. So remember, this alpha parameter was what told us basically what our conductivity was. So our conductivity should be alpha divided by F, and our kinetic inductance will then be dependent on the dimensions of our structure as well as that alpha parameter. So we can go ahead and calculate what that alpha is for this given superconductor. We find it's some random value, but it's 2.66 times 10 to the plus 17 hertz times ohm per meter. We can then calculate how the frequency is going to shift associated with that change in kinetic inductance. So the frequency of the shifted resonator will now have an additional inductance compared to the what we were just simulating. So you can look at the ratio of these two. Basically, what you can express them in is terms of this beta parameter, which is the ratio between the kinetic inductance and the geometric inductance. We can calculate that for this microstrip resonator. I got something like 2.27, which I'm expecting that should change our frequency to about 55 gigahertz. So it's actually going to change our frequency quite significantly, more or less by a factor of 2. Okay, so let's see how we actually do that in COMSOL in the last few minutes I have here. So first thing I need to do is I need to include the resistivity of the aluminum. So this I'm going to give in 1/Siemens per meter. So this is 100 micro centimeters, which it'll convert to ohm centimeters. So it's ohm meters over here, which is a good unit for resistivity. We then want our critical temperature. COMSOL knows how to do Kelvin as well, so 2.3 Kelvin. And then finally, we have this alpha parameter. So I'm going to express it in terms of, excuse me, there's a built-in constant. So if I do KB const, that's just Boltzmann's constant. Some other constants. So H is Planck's constant. And then we also have speed of light, which is, C const. So just to show you that these, prove to you that these constants are what we expect them to be. I'm going to use those in a second. Basically, got KB const times TC divided by 0.18 times H. So this is just the alpha parameter from the slides I'm coding in. Good, so it's a 2.66 times 10 to the 17 that we expected. I'm actually going to do this beta parameter as well. So that was C divided by speed of light divided by 120 times pi times alpha times width times thickness. And then we had that logarithm of the 8 times the ground plane separation divided by the width. And so 2.27 was what I calculated before. And then the frequency ratio was just the change in frequency. So it was just 1 divided by 1 plus beta. Good. So this is telling me that the frequency should go down by about a factor of 0.55. We targeted 100 gigahertz. So we're going to get roughly 55 gigahertz as our solution frequency. Okay, so we have our superconducting materials and parameters. We then have to actually change that for our superconductor. So what we need to do in COMSOL is we basically, I've already done this part here where I've made this parameter, but now we need to go and change our conductivity to emulate that superconducting conductivity. So we need to make our sigma 2 equal to this value. So we need a minus ij times this sigma 2. So we put that in our superconducting material. I'll expand that so it's easier to see. So COMSOL, we need to do basically 1j is I times alpha divided by, and then to access the frequency of our system, we need to do EMW. So that's the solver, and then freq, and that gives us the frequency. Okay, there's one last thing we need to do before we move on, and that is we need to go into our solver, and we actually need to change where we're basically looking for frequencies around. So normally it's looking around 0 gigahertz, but what we need to do for this system is because we put in a frequency dependent parameter into our materials, we actually need to basically iteratively change this value here in order to get close to our frequency. So we know we expect something to be roughly around 55 gigahertz. So let's put 55 gigahertz in, then start the simulator. So what's going to happen is, or what normally is going to happen is you're going to get close. We've got a close guess. So 55 gigahertz is going to be close to the eigenfrequency we solve here. What we actually need to do is we need to tweak that a little bit in order to iteratively get closer and closer to our actual frequency. So you can see here that the frequency we solved was 50.365 gigahertz, but that was the solution if we had assumed our frequency for our material was 55. So what we need to do is change that. So let's get a little bit closer to 50, and so we can sort of iteratively change that number in order to get closer and closer to what the actual solution will be. Oh, sorry, hit compute. So now if I put 52 in for my linearization point, I'm hoping this number will get close to 52, and we'll be able to sort of tune in and sort of play a game where we slowly work towards the actual frequency of our device. And so this is a little bit of an annoying process that needs to be done. So ends up I got very close. I kind of knew what I was expecting. So now it's 52.025. If I really wanted to, I could go in here and continue changing this. I could go like 55.02 and slowly and sort of arbitrarily get as close as I wanted to some frequency. So I'm running a little short of time here. So one thing I just want to point out though is now as we realized with our calculations, what we found is that excuse me, our kinetic inductance or our frequency basically now depends very strongly on the non-length or sort of the cross section of our microstrip. So the width and the thickness now actually matter quite a bit. So if I were to say change the thickness to say 50 nanometers, my numbers basically all change. So I'm expecting something closer to like 40 gigahertz now. So if I go into my solver, I have to put that 42 gigahertz into here and compute it. And so what we're going to see now is because we have kinetic inductance, our lateral parameters or our geometry parameters, so our width and our thickness, which set the cross section of our resonator, now actually matter quite a bit more. So this is something that's very important when you're actually fabricating these devices. Basically, because so now this is 38, so I can play that game again where I go in and let's say I change this now to 40, get a little closer. But basically, what I was trying to say is when we're designing these devices, the dimensions actually matter a lot, which is a bit challenging because it's hard to know exactly what you're going to get when you go in the clean room and make these devices, but you generally take your best guess and try to hit those targets as best as possible to make your device. So now we're getting closer. So it's something around 40 gigahertz now, whereas before it's 55. So I guess one big thing one take home message I want to have from this is that you really need to, if you're simulating devices that have kinetic inductance, you really need to take that into account when you're simulating them. And I've sort of tried to show a way how you can do that in COMSOL. So with that, we'll go back to the slides. I'm basically done. I'll just go through sort of quick conclusion slide. Talked about superconductors that, in a lot of cases often have this additional kinetic inductance due to the inertial massive charge carriers, which is important and actually changes our results. We care about this for a number of different materials that can be used for different applications like detectors, amplifiers, and qubits. What I really want to stress is that in these materials, kinetic inductance must be accounted for in order to accurately model the behavior of these structures. And we can do that by basically tricking COMSOL. So COMSOL doesn't really normally deal with superconductors, but we can trick it by using this imaginary conductivity in a way that we know will behave like a superconductor in order to do these superconductor simulations. Yeah, so with that, I'd just like to thank you for your attention. Thank you for all for coming today and listening. I just want to point out that we've got a small group here at the University of Waterloo, but we're definitely growing. So we're looking to hire talented students and postdocs. So if anyone's interested in the stuff I talked about today, or we do a lot of other things that was mentioned early on, like optomechanics and other things related to superconducting circuits. But feel free to reach out if you have interest. I'm happy to chat with anyone. But yeah, thank you for your attention, and I'm happy to take any questions.
Thank you, Dr. Howard, for such a great lecture. We do have some questions. Question number one, what electronic devices besides amplifiers can be constructed using the nonlinear kinetic inductance of superconductors?
Yeah, so besides amplifiers, was that the question?
Besides amplifiers, yes.
Yeah. So on that one slide, yeah, here I talked a little bit. So amplifiers is a big one. Lots of people are interested in what calling these. They're calling them kind of KI amplifiers. So like for instance, there's these JPAs, traveling wave parametric amplifiers. So they're calling them KI traveling wave parametric amplifiers or KOI TUPAs. They're a hot topic of research, but there are different things I talked about before. So actually, the original application of the kinetic inductance was often in detectors, so microwave and other photonic detectors. So kinetic inductance, because of this nonlinearity, is very, very sensitive to detecting single photons in these regimes or photons in the regimes, as well as qubits. So you can actually use that nonlinearity to create qubits. So those are the big ones that I'm aware of. I'm sure there's other ones or more that people will come up with. I know you can actually use them to make what we call superinductors, which are basically just it's a fancy way of saying you get added inductance. So you can make more inductance per unit length. So you can make your inductors smaller and you have smaller footprints. So that's helpful. The downside is you have to have a superconductor, so you have to be operating at cryogenic temperatures in order for any of this to be going on. So, for example, for niobium titanium nitride, which is generally one of the higher critical temperature superconductors, you still need to get down to something below 17 Kelvin, and you probably be quite below. So you probably be close to like 1 Kelvin still for these types of systems. So there is that caveat there, but that's a lot of where people are operating these quantum systems nowadays. So some people don't mind being able to having to go to those low temperatures to get these good properties. Hopefully that answers the question.
Okay, thank you so much for answering. The second question, are we able to import materials from outside, like doped materials or composite materials?
In COMSOL, is that the idea? So
Yeah. Okay.
yeah, I assume they mean in COMSOL. So let's see. There's I was basically just building my own materials, so I was just going off blank materials. Looks so a couple of things I'll say here. So there's an entire material library that COMSOL has. So some of these are associated with specific modules, and so you have to buy a specific package or include a specific package. But there's a whole bunch of built-in um, materials. So example like American red oak for whatever reason is on here, but like aluminum, alumina, air, all sorts of different stuff and sort of simple materials. But then you can get into sort of more detailed. So I think there's like RF materials. So they've got things like, I don't know, like Corning fiber and stuff like that. But uh, so the console does have its own built-in stuff, but then it also looks like I've never done this before, but it looks like you'd actually import materials. So there is a functionality to import materials. I don't know exactly how that works or the way that that would be used for these composite materials you're talking about. But I imagine if you were to look on console or talk to someone from console, they'd be able to tell you how you could import these materials that are you're talking about.
Okay, the third question, can we customize the geometries?
Yeah. So the geometries are completely customizable. You can go and you can do. I didn't show up. There's this thing called work planes. So you can go into a plane and you can actually just sort of draw geometries and then build them out. So it's very similar to CAD software. So you can mix curves and lines and rectangles, circles, and ellipses. One thing that's actually interesting as well for this is you can there's let's see if I can find it. Yeah, there's actually an import function for geometries as well. So you can import, 3D CAD files. You can import. I think they actually let you import GDS files as well for layouts, or I mean that's ECAD. But basically, you can import any sort of or all sorts of different CAD files as well. And there's actually ways of linking between different types of CAD software. So if there's something you feel like you can't actually build using the interface in console, you can always build it in an external CAD software and then import that through this module. I think that requires a separate module, or I'm not exactly sure how that works, but yeah, there's definitely possibilities to sort of build any sort of geometry you're really interested in or able to make in a CAD software essentially.
Okay, and the fourth question is, how does high kinetic inductance make a superconductor more suitable to be used as a qubit? Only because of higher impedance, or are there more properties which follow with high kinetic inductance?
Yeah, so you will get the higher impedance, which is sometimes useful. What I guess the main thing you get from the kinetic inductance is the nonlinearity. So when we make these superconducting circuits, you need this nonlinearity in order to create a anharmonic resonator. So generally, historically, what that's been provided by are these Josephson junctions. So these Josephson junctions are also nonlinear inductive elements. They are generally quite challenging to make. So people have been looking for ways to get around that. And so the main thing for the kinetic inductance is it has a different type of nonlinearity, but it's still a nonlinearity. So once you introduce this nonlinearity into a resonator structure, you'll basically create this anharmonicity, which allows you to then address basically two individual states at a time without exciting it into this ladder of excited states. So you can basically, use it as a qubit and say the ground and excited state are your 0 and 1 state. So it's really this nonlinearity, which is the important part for generating that for making qubits out of these types of systems.
Okay, and why imaginary conductivity is considered in COMSOL?
Sorry, what was the? Okay, can you quick catch that?
Why imaginary conductivity is considered in COMSOL?
Why is the imaginary connectivity considered console? So I think the question is asking why did we put an imaginary connectivity into console? So the answer is basically if you go back to this slide here. So generally in console, what we want is it's thinking about conventional conductors or normal metals. In which case we're going to use just a real conductivity, which is what most people kind of expect for sort of everyday sort of metals. So in this case, you put this here. What we decided though was that for superconductors, what we actually want is the sigma one to be close to zero, which gives us this property that the charge carriers or the Cooper pairs in these structures can flow with very little or no resistance. And then what we wanted was this, excuse me, this imaginary part to be non-zero, and that basically is a result of this Mattis-Bardeen theory. So this is an extension to the BCS theory of superconductors to higher frequencies. And what you find is that you get exactly that situation where this real part is zero and the imaginary part is non-zero, and that's what causes both this low loss flow of current as well as the kinetic inductance. And that's just basically a fundamental property of superconductors. This is always going to happen to some extent, and then the extent to which it happens is going to be dependent on the superconductor. And so for these high kinetic inductance superconductors, these effects are much, much larger. Hopefully that answers the question.
Yeah, that answers it great. The last question we have, you built the airbox on top of the substrate. Why not the substrate inside the airbox? And why machine the airbox?
What was the last part of that question? Sorry.
Why machine the airbox?
Why machine the airbox? Um,
Machine.
okay, so I guess the question is sort of surrounded on why do we, yeah, that. Why did we include this airbox in our structure? So, and why do we build like we did? Why did we put a substrate and then on top of that an airbox? So the answer is we basically need to try to emulate as much as possible what this actual device is going to look like. So I'm imagining that this is, this would be some device that would be on some very, very large chip. And I'm only just going to zoom in and narrow in on a very, very small slice of it. So what I'm looking at is some slice of this chip. And so I can't simulate this entire chip because I basically don't have the computational power to make the mesh big enough in order to do that. So what I need to do is sort of trick COMSOL into thinking about a small segment of this piece of wafer or this piece of chip that we're going to now simulate. So in this case, I'm thinking of just a slice where I've got some air above it and then some substrate below it. I could have made this bigger in either direction, but I'm imagining there would be more in a real device. There'd be more substrate out this way, so I can't really surround this in air because that wouldn't be realistic for what I'm trying to simulate. Um, Also, I guess the other part of the question is, I guess why machine this air or why does this airbox need to exist? If I didn't have this, I wouldn't really have anywhere for the fields to expand it to in this area. So I really need to have this bit of air above or vacuum or air, how you think about it, above the substrate below, and that allows the fields to sort of extend in all different directions in a way that we'd expect for this type of device. Hopefully, again, that
We do
answers.
have one more question. What
Yeah.
is a granular aluminum? Are there other types of aluminum available for superconducting qubits?
What? Okay. Let's see. What is granular aluminum? So granular aluminum is again what I talked about on this slide. So this is aluminum that instead of just depositing pure aluminum in a vacuum, what we do is we co-deposit it in an oxygen environment so that we form pure aluminum islands that live in an aluminum oxide matrix. So it's both aluminum and aluminum oxide. So it's these little granular pieces of aluminum. That's why they call it granular aluminum. And yeah, so that you can tune this resistivity parameter or tune this disorder parameter to change the conductivity. Um, do we have other types of aluminum for superconducting qubits? I suppose the answer is yes. There's pure aluminum, but there's also lots of different types of alloys of aluminum. So I think there's one called 6061 or something that was kind of the typical aluminum, but there's a number of different alloys which could be used. They all go superconducting. They go superconducting at different temperatures. I'm not sure if there's any advantages to using those alloys over pure aluminum, for instance. For what I know, for the most part, people generally just use pure aluminum. But I suppose there might be some advantages to using some sort of different alloys, but not that I'm aware of.
Okay, thank you so much for this great lecture, Professor Howard. Thank you for taking the time. And
Yeah,
now we can,
thank you for inviting me. It was great.
okay, thank you. Goodbye. We can now move
Thanks.
on for our second lecture. We have Sadman Ahmed Chantu, and he's going to continue on tutorials on squads. So welcome. Hi.
Great. Everyone, thank you, Professor Hara, for a great talk. I will continue on my tutorial series from the last 2 days. Okay, let me share my screen. Just one confirmation that the screen is being shared.
Yes, it's being shared, yes.
Awesome. Cool. So the tutorial for today is essentially to learn how we can use squads as a database for generating training data sets to do some machine learning interpolation. And I kind of wanted to start out by reviewing a slide from Eli's talk about the need for interpolation within our project. So what you're looking at over here are essentially some of the simulated data points from the database. And let's say you want a design that has Hamiltonian parameters that land where these red crosses land. Of course, as y'all have seen over the last 2 days, squads will give you the closest simulated design that correspond to your target, right? But let's say you're not happy with this. Let's say you wanted a result that matches or that lands on the point that you were querying for, which in this case, as you can see, it's not possible because we didn't have a simulation that had this exact same parameters. So this is the motivation behind interpolation. So we wanted to essentially use the information that we had in our database and figure out how we can interpolate our designs or how we can interpolate on the Hamiltonian parameters space to get you back a set of design space variables that matches your query parameters. And this is something we talk about in the paper, how we do it. And I also have it over here. It is long, it is complicated, but it works really well, as we have shown in the paper. And a big limiting point for this interpolation algorithm is that it's very device specific and it's very design specific. For example, this interpolation algorithm only works if you're dealing with a trans-1 cross with the claw and a CPW resonator. That's it. That's the only case where it works. So this is not something that you can scale up to other geometries, sadly. So this further motivates the need for an arbitrary physics-inspired interpolation algorithm. And we thought about this for a little bit, and it's a very tough problem. It's very tough to go from, a general point in design space to its mapping in the Hamiltonian space. So this is essentially what a simulation does, if you think about it, right? It just maps you from what your design is to your Hamiltonian. But it's a very tough problem. But since we have data on both of these disconnected spaces, this is a great application of machine learning to figure out how to simulate the simulator in this case. And that's what we will kind of talk about today. But firstly, before we throw the kitchen sink of machine learning at this problem, we wanted to first see if there's any learnable structures in our data or not, which, as you can see from this 2D UMAP projection, there are some learnable structures. So that was verification number one. And if you do some literature research, you'll see that a paper by Nugraha from, I think, 2022, he has shown that you can indeed do this for qubit geometries. Let's say if you only have qubit parameters, such as qubit frequency, you can kind of trace back the geometry parameters needed for the qubit to get that qubit frequency. So it's a nice work. But I did try this neural network on my data set where we have, again, multidimensional spaces on each end, and it doesn't work that great, but it still works pretty decent for its use case, of course. And this is some result I had, again, almost a year ago. It's basically a very, very basic black box random forest regressor. And I've trained it on, again, since it's a year ago, the training data set was actually much smaller than what it is right now. But the 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 takeaway point is that, as you can see from these graphs, the machine learning curve actually does follow the trends in our physics-based interpolation algorithm. So it does capture the physics of the problem, which is really great. And this, again, this is a very, very simple model, which took like 8 minutes to train. So of course, one can do better on this. So the objective for today's tutorial is to essentially, again, learn how to use squads to create a data set for machine learning application. And then we're going to train a simple machine learning model on this data set. And then we'll talk about how we can evaluate the machine learning model, how to simulate it, and how to benchmark it, and how to deploy this machine learning model so that other people can use it for interpolation use cases. Let me now share my Jupyter notebook. Okay. I believe I'm sharing. Okay. So as we have done for the last 2 days, we're going to import these handy modules and import the squads DB and analyzer objects from squads. We will also query the database and create this system with qubit and cavity claw, as we've been doing for the last couple of days. Specifying the system, we will have a transmon cross and a route meander CPW, which is quarter wavelength. And then we use this create system data frame to create our combined data set. Pass this on to our analyzer object. Okay, so right now what I'm doing over here is we want to first generate a complete training data set. And as y'all may recall from the last 2 lectures, to generate this complete data set, we need to give it some target parameters. So for today's tutorial, I've generated some really demo and random target parameters that I'm going to be feeding to this method that we have in squads called generate qubit cavity training data. And what it will do is essentially it will return back a data frame that contains information for all the design space variables that we have in its corresponding Hamiltonian mapping that we can then use to train a model. So this method is basically doing the work for us. So let's run it. Cool. It also saved the dataset file so that if the kernel crashes or something, you'll have access to it. Let's look at what this looks like. So it has 133,000 entries and 13 columns. And these columns are essentially, as you'll see, claw length, cross length, cross gap, ground spacing, coupling length, and total length. These are the design space variables for this system. And cavity frequency, kappa, EC, EJ, qubit frequency, and harmonicity and G. These are the Hamiltonian space variables for this system. So this basically, this training data frame object is the data set that we're going to use to train a model. Okay, perfect. So now we're going to start. And again, before we train the model, we need to do some pre-processing because all these variables have their own units and stuff, and you would always want to make sure the units are kind of unitless and normalized when you train a model to get accurate results. So I have different environments to do my training and my squad stuff. So I just changed to my training environment. Again, importing all the usual suspects in the machine learning world, such as sklearn, TensorFlow, and even Hugging Face here, doing all that. Takes a second, apparently. Okay, cool. All right, let's read back the training data frame since I changed the environments. Cool. Now, again, all these data sets from squads, there's no duplicate data really. So we don't necessarily need to do this, but I'm still dropping all the duplicate data and resetting the index. Again, it's all already reset, but let's just do it for sanity, for sake of our sanity. Let's do that. Cool. Now that we have our training data frame, we would now want to separate it out to our feature set, which I'm calling X in this case, and our target set, which I'm calling Y in this case. Again, remember, the idea is that this black box machine learning model, we will be able to give it some Hamiltonian parameters corresponding to these, Hamiltonian parameter values corresponding to these parameters, and it will give us back the geometry space values corresponding to these parameters. So that's the name of the game we're trying to play. So let's make this separation. Awesome. Now, of course, for doing any machine learning training, we need to separate out the training and the validation test data sets within the training data set. So we use this method to do so. And now we want to essentially create or increase the size of our feature set so that the machine learning model can capture the nonlinearity in our data set. So just to, I'm not too sure how familiar y'all are with machine learning lingo, so it might be very trivial if y'all already know it, but just to give a quick introduction, this polynomial features, what it's doing is, I'm doing a polynomial feature degree 3, right? So essentially, if my feature set right now has cross length, claw length, coupling length, total length, and ground spacing, right? Degree 2 would mean that I would also include cross length square, claw length square, coupling square, total length square, ground spacing square, and also cross length times claw length, cross length times coupling length, cross length times total length, cross length times ground spacing. So it's essentially expanding on the feature set so that any target space variable that is explained by the polynomial relationship between the feature set can get captured. So it's a good practice to do so. So I am doing a degree 3 in this case, so it's going to be multiplying each thing by 3 times and also include the cubic features as well. And this include bias equals false means that I'm not keeping the constant terms, so that's not really relevant. Cool. Let's now look at what the new training data shape would look like. As you can see, the original one, okay, this is a fewer entries than the initial training DF that we provided it. It's because we have separated that out into a training and a testing one, but it had 5 columns, right? That's what we have for our design space variables. Oh, sorry, our Hamiltonian space variables. But as you can notice, for this new updated training features, we have 55 columns, and it's because we are doing this n plus d choose d polynomial, which actually in this case is 8 choose 3, so it should be 56. But since I'm not including the bias point, it's 55 columns. So that's what it means. Now, of course, as I kind of mentioned earlier, each of our features have a different unit, a different dimension, and we don't want that. We want to normalize everything. So for that, we are using the standard scalar module to make it unitless and make sure everything's normalized in the both X and Y dimensions. Done that. And now let's define the model again. Since this is something we want to do live, let's make it a very simple model. It's a 3-layer system. Again, I very arbitrarily chose these numbers from, again, textbook. It's a very textbook model, textbook numbers. So first layer has 256 neurons, second one has 128 neurons, third one has 64 neurons. All of them use the ReLU activation function, applied some batch normalization, some dropout numbers. Again, very, very textbook. You'll see this. So, and I think I'm using the mean squared error as my loss metric here and the atom optimizer. So now, okay. We will train this model for 500 epochs, but I have included 2 checkpoints, one for saving the model whenever the best one. Always saving the model after each training epoch, only keeping the best model. It's something I would always recommend everyone for every single machine learning task to keep. I have in the past very embarrassingly not included this for tasks where I should have included this, so don't make the same mistakes as me. This early stopping checkpoint essentially means that if once your training has kind of saturated, you stop it. It's no need to waste your computational resources. So let's start training this model. And since I think it's going to take like 2 minutes to train, so I can take some questions if there are any so far while it's training.
There are no questions so far. Maybe you can continue. I think everything's good.
I'll just have to wait. It's going to take 2 minutes to train the model. So and this model will not perform super well. It's because again, it's a very simple model, and just for the sake of the tutorial, I chose something that trains fast. We'll still see that it does hopefully somewhat of a decent job. Should be done soonish. Is today the last day of tutorials for this week?
No, it's the last day is on the 20th October.
I see. Cool. And the team formation has to be done by then.
Yes. The team formation has to be done, and they have until the 15th of November, I think, until they can, finish their projects. And
Is
we're gonna
everyone
show
required to be?
everything is required. What?
So are all participants required to be in teams, or it's just people who want to do a project?
They can do it individually, yeah.
Oh, I
If
see,
they,
see. But everyone is required to.
but it's like encouraged to have teams.
I see.
Maybe I can take this one.
It's encouraged to have teams, but maximum 5 people.
I see. Sounds good. Okay, the model has been trained. Took 115 epochs and 2 minutes. Cool. Let's see how the training looks like, or training looked like. This is the figure. Yeah, as we can see, it started again. It's not ideal, but it's something. It learned something. Let's evaluate this model based on the validated or the test data set that we had. Let's see how it looks like. Okay, let's see. So not great, as it's obvious. It picks up sort of well on the cross length, tall length, and the maybe I can claim the total length variable. It picks up sort of well, but the ground spacing one, it does not do a very good job. And even in the coupling length part, sort of decent. But again, I need to emphasize that this is a very, very simple model and it only took 2 minutes to train. So we could not expect it to be that great anyways, but it's promising that based on this uh, very simplistic model, we can at least still pick up general trends in the data. So that's sort of nice, I guess. I have some more test data that I'm going to read in over here. This is, again, I included this test data set because I have what the prediction for our physics-inspired interpolation model is for these numbers. So I want to compare my physics numbers to these machine learning model numbers to see how they look like. So let me do that. I'm reading the interpolated one, and I also have the numbers that the data set, essentially the closest design space variables for the queried Hamiltonian parameters in the data set. I'm going to read that and compare the machine learning numbers to that as well. Let's see. Okay, as we kind of already could tell that it does very nicely pick up on the physics of the scaling laws of the cross length and the coupling length actually fairly well here, the total length-ish, but the ground spacing, it does not really do that great of a job. Again, it took only 2 minutes to train, so I think it's sort of nice. So now that we know how to train a model, let's learn on how to simulate and benchmark the model. So for that, I'm going to go back into my squads environment, rerun these cells. And what I'm trying to do over here is essentially, okay, let's talk about the idea. The idea is that, okay, fine. I found these numbers, these design space variables from a machine learning model, right? And of course, as y'all can kind of see, a good way of benchmarking how good this machine learning interpolation is to compare it to the corresponding physics-based interpolator. And the idea is, and since we have shown in our paper the physics-based interpolator works really well, if it matches the numbers of the physics-based interpolator, you don't necessarily need to simulate the design that these numbers provide to see where it lands in the Hamiltonian space. But of course, once you simulate that, that is without any, what do you call it? Without any doubt, that is the more accurate figure of merit, right? But I just wanted to explicitly point out that the simulation is not necessary if you just compare with the corresponding physics-based interpolation results for those target Hamiltonian points. But in this part, we are basically trying to use these prediction numbers and simulate each of these systems and see where it lands in the Hamiltonian space. Okay. So I am again reading everything since it's a different environment. And for doing so in squads, we have this nice method called get design for ML prediction, where you just again pass on the analyzer object that you created the system with, your test data that you want to test against, and your prediction data and your prediction data, yes, that you want to get the designs for that you want to then run simulations on. So let's do that. Okay, cool. As you can see, this is in the same form as we have had in the last 2 days, where you are given the information on the design options dictionary that, as we've shown in the last 2 tutorials, that you can then use to create the corresponding Qiskit metal design for it, and then run. You can create the corresponding Qiskit metal designs, and then as I'll show you, we can then run those designs to get the simulation results. After which we can do some Hamiltonian analysis on it to get back our target, to get back the Hamiltonian parameters that we're interested in. So for this, for doing the simulations with ANSYS, because that's what we support right now, you just import the ANSYS simulator from Squads. And then again, I cannot run ANSYS right now because I'm on my Mac, but everyone who has a Windows and has the ANSYS license can then just run this code block, and it will basically run the simulation, extract the Hamiltonian parameters, and then save it in this hparamesimd variable, or hparamesimd list, and that basically then is what you can use to compare how far the Hamiltonian parameters for the machine learning interpolated case are from the target ones. So this is what this code block is doing. Again, just to give you all some familiarity with the API, you pass on the analyzer object to this ANSYS simulator class, and then you give it the design space, or each data frame from the design space. So each line over here, you give it that, since we have like 6 of them. And then the idea is that you just run the simulate method on this data frame, and it will extract out the relevant eigenmodes, the relevant capacitance matrices and stuff, and also it will calculate the 5 Hamiltonian parameters of interest for us and give you back that. So that's what this code is doing. And I'll still run this code block, but it will tell me that, okay, you don't have ANSYS installed on your computer. So it's doing what it's supposed to do, but it would work on people who have the ANSYS license and a Windows machine. Now, I understand a lot of people don't have an ANSYS license, and that's totally okay. Actually, before I talk about that, let's kind of show you what this model. So I think a couple nights back, I had the same three deep layer model, but with its hyperparameter optimized. I used that model, and then I ran the simulations that this model kind of gave us. And as y'all can see, for the case of the G alpha, this red cross is what the target or the user wanted in terms of its Hamiltonian parameters. The green ones are what was found in the database. So as you can see, the green ones are already a lot better than the purple ones, which are the simulated results based on the prediction of the machine learning model. So yeah, in all cases, the database was dense enough to give us a better result from the closest point, and the simulations were kind of not the greatest. However, that picture kind of changes in the kappa cavity frequency space, subspace, where as y'all can see, in most cases, actually, the machine learning models prediction for where or the machine learning models predictions for what the simulation geometry should be is actually much better than the closest found or closest possible design space variable, which makes sense because the kappa cavity frequency space for our case is a little bit more sparse compared to this space. So that's pretty cool that even with this simple parameter, you get something at least. Okay, now back to the thing I was talking about. So I understand as it's expensive, we don't have access to it, but in the next series of squads, you will get access to running these simulations and doing the Hamiltonian analysis with Pallas. And how we do that is we do it with this tool called SQD Metal. It's a tool made by our collaborators from the SQD lab, and it's essentially a wrapper between Qiskit Metal and Pallas that aids in the simulations, going from Qiskit Metal, creating the mesh, and then running the simulation in Pallas. So right now, sadly we couldn't have a super accurate version ready up until literally last night at 1:30 a.m. I got a message from the people in Australia, but of course I was dead asleep at that time, so I didn't get the chance to add that code cell right now. But I will update it hopefully end of day today and post it in the updated tutorial repository and also the doc site for squads. So keep an eye out for that. But I wanted to kind of give SQD Metal a shout out and kind of show y'all what they do. So firstly, again, let me actually, I feel like I'm jumping the gun. Let's talk about Pallas a little bit. Let me share my screen again to a different window. Okay, so this is Pallas. Pallas is essentially kind of like ANSYS, kind of like Console, but it is a free tool, and it can do what ANSYS and Console can do, not as well as both of them really, because it's open source and it's free, but it's actually pretty decent. And one of the nice things about Pallas is it's HPC native, so it can scale really well and handle bigger workloads. And it has pretty decent documentation of how one can use to run simulations within Pallas. So I would encourage y'all to look into that. But one thing I would say is installing Pallas is not as simple as doing SPAC install Pallas on your local machine. But don't worry about that, since I have pretty decent documentation on our squads doc site for how you can install Pallas on both Macs, Linux, and Windows machines. So I would encourage y'all to do that. But Pallas is the tool for running simulations. Kind of wanted to show you all that. Second is the SQD Metal that I was talking about. So this is their GitHub repo. They have decent documentation of how to use them as well. But for right now, I wanted to show y'all how you can run your simulations with through SQD Metal using Pallas. So they have documentation of, again, how to install them. You can disregard everything up until this point, because you can use the squad's doc site to install Pallas. But then this is a code log that kind of shows you how you can set up Pallas to run a eigenmode simulation, for instance. They also added these new Jupyter notebooks, which has a more comprehensive. This is actually an example based on my design, where, as you can see, this is actually these numbers were retrieved from squads. This is the transmission line. This is the quarter-wave resonator hanging across it, and this is essentially showing you that the eigenmode is localized here. So that's one of the eigenmodes. So this Pallas simulations, I would encourage you all to play with this and learn about this. The second one is essentially to use Pallas to extract the capacitance matrix of a trans-1 coupled to a transmission line. So they have code for that as well. But again, hopefully by the end of the day, or at least by the end of the week, I will update my tutorial for y'all with API that integrates SQD Metal and runs it within squads. So that's something I will work on. And also, last thing is, as Professor Howard mentioned in his talk, in console, you can import geometries from Python or from any arbitrary systems. Like, it doesn't necessarily have to be from, let's say, a GDS file. So SQD Metal also has documentation on how you can, again, create a geometry in Qiskit metal, but then create a mesh using Console that you can then run it in Console. So this is the code needed for that. So it's a pretty really cool tool as well. I would encourage you all to look into them. Now let's go back to my tutorials. Okay. So I have the relevant links here. And lastly, the last thing is, let's say you create some better model than the simple model and it works really well. You would want to share this model with me and the rest of the squad's community. And there's this and Hugging Face has this really nice integration with TensorFlow where you can just import this load module from TensorFlow and run this two commands, load model and save. And in the save command, you basically, you need to create a Hugging Face account, of course, and you pass in your Hugging Face username and your model name, and you run this cell. And, oh, actually, I think I did not. I'm in the wrong environment. That's what's going on. Sorry. Let me interrupt this. Could we? Yeah. It will take like 3 seconds when it works. Not 3 seconds, but 9 seconds. But yeah, that's it. It basically uploaded your trained machine learning model to Hugging Face, and anyone can then essentially use your model by calling keras.savingmodel.loadModel from your repo. So they make machine learning very accessible, honestly. So it's super nice. And I would highly encourage that, let's say, in your project or in your own experience or in your own time when you're playing with such models on squads, if you find a model that's really, really, really good, email me. I want to see it and I want to add it to the squad's ML model collection. So I want to say that. This actually is my last tutorial and it's in the last stage of it. So I kind of wanted to tell you all that please contribute to squads. You've learned a lot about it and there's a lot that y'all can contribute towards. So please consider that. Secondly, best of luck with your final project. It's been really fun getting to know y'all and teaching y'all some stuff about squads. Very excited to see what you all work on. And a shout out for our department. USC's physics PhD program is free now. Everyone can apply. You don't have to pay any money for it. The deadline is December 15th. We have it's a great school. We have great facilities within physics and electrical engineering, and especially in quantum information sciences. It's really exceptional. Our lab in particular, the Levinson-Polk lab, we work on various superconducting quantum devices. That's, of course, not only software-based, but we have our own lab processes, own devices, own experiments. I would encourage you all to click this link and learn more about our lab. We do take 1 or 2 PhD students every year, so be my colleague, apply here. And also, we are looking for a postdoc, so if any of that is relevant to you, please consider applying. Yeah, Eli is a great, amazing scientist, but I think more importantly, he's a great human. So again, apply to USC and to our lab. That's the end of the tutorial. I'll take questions.
I think there are no questions for today, but if anyone has a question, we can actually share it on the Discord channel later.
Yeah.
Or you can answer it.
I'll get back to you all. Sounds good.
Okay, thank you so much for today, and thank you for all the tutorials. Everything was so great. Thank you.
First, thank you all for inviting me.